Hello guys, so in today's video we're going to go over Dijkstra's algorithm. Dijkstra's algorithm is an algorithm used to find the shortest distance between any two nodes in a graph. So here the circles with the letters in them are the nodes, and the edges are represented by the lines between the nodes, and each of these edges has a weight, or we can think about it as a distance, between the nodes associated with it. So in this episode we're going to try to find the distance between the A, the start node, and the G, the finish node. The way Dijkstra's algorithm works is by looking at all the nodes that we have found the shortest path to already, and then expanding our knowledge of the graph by looking at the adjacent nodes. So how does this look like? We're going to organize this in a table where we have the node names, the distance to the start, and the previous node visited on the path. So obviously A is our start node, and the distance back to the start is 0, and there's no previous node. And now when we already guarantee that we found the shortest path to that node, we're just going to write a little check mark next to the node name, meaning that we know the shortest path to that node already. And once we have found the shortest path to A, we can now visit its adjacent nodes and update the distance to them. So the distance to C is 3, the distance to D is 2, and the distance to B is 4. Remember, this is all from A, and we're going to set the previous to be A as well. Now, which one of these can we guarantee that we found the shortest path to already? At each step of the algorithm, we can adjust the nodes to be known that we know the shortest path if they have the smallest distance. So in this case, D, we can check off and guarantee that we found the shortest path. Now, why is this? B and C we can't guarantee has the shortest path because D has a smaller distance back to A, meaning that since we haven't checked D yet, which we're about to do, that there could be a path through D that reaches B and C faster. So let's go through D and do this exact update, and we'll see that B now has a shorter path of 3, and it's through D. And now for C, the path would be 6, so we don't update it. The shortest path is already through A. Now through F, we've found a new shorter path, and remember this is a cumulative distance, so the path length is 5, and the distance is, and then we go through D. For G, there's a distance of 7, and again through D. And for E, we found a distance of 3, all through D. Okay, so now what's the next node that we can mark as known, that we've already are guaranteed to have found the shortest path? So we could do it for any one of B, C, or E. In this example, I'm just going to choose C, but it doesn't matter. When you have nodes that are equal in step, you can choose any of them. So we chose C, and now we're going to visit the adjacent nodes to C, updating only the ones that we found a shorter distance. So A is already known, we don't do anything. D is already known, we don't do anything. F, we found a path of 4, so we can update it going through C. Now let's go to the next node, and let's just choose E, for example. Again, we could choose between B and E, because these are the ones with the shortest distance, and that are unknown so far. So let's just go with E. So let's go through E's neighbors. B this would be a longer path. This would be a path of 8, but we already have a distance of 3. D is already known, and G, we actually find a path of 6 to G through E. Now, even though we've gotten to G, again, we can't finish yet because we're not sure that 6 is the shortest path through G. Since B has a smaller distance, there could theoretically still be a path through B that we haven't looked at yet, since we haven't said that B is known as well. So we can't mark off G as done yet, and we have to keep going through our algorithm. We're going to mark B off as known, and we're going to go through the neighboring nodes. No updates to be done to A, no updates to be done to D, no updates to be done to E either, since they're all known. And we're going to keep going. F, this is the smallest distance at all the unknown ones, so we're going to mark it off as true. And no updates to be done here either, since this path would be 11, which is longer than G's 6. And now, finally, since G is the smallest distance out of all the ones that are unknown, we can mark it off as known, and we can finish Dijkstra's algorithm on this entire graph. So how do we actually build the path from this table? We read the table backwards, starting at G, and we go to its previous node, E, write down E, go to E's previous node, write down D, D's previous node, and write down A. And once we get to A, which is our start node, we have found the shortest path from A to G in this graph. Of note, we have also found the shortest path from A to every other node in this graph. We have found the shortest path from A to B, from A to C, and from A to every single other node. Another thing to note is that Dijkstra's algorithm only works on graphs that have non-negative weights. We're going to see how this -5 messes up all of Dijkstra's algorithm. Starting off at A, we would update C to have a distance of 1, and B to have a distance of 3, all coming from A. Then C would be marked as known, and then we would proceed from C. And then the issue that we see here is that this loop will keep acquiring negative distance. So we could go around this loop an infinite number of times, and get as small of a distance as possible, and then go to D. So there's no real shortest path here. You would just get stuck in this cycle going around this loop. So thanks so much for watching, guys. If you guys have any questions, leave them in the comments down below, and let me know what other types of videos you guys want me to make in the future. Thank you.